I work at the Royal Institute of Technology in Stockholm, at the Supercomputer Center, PDC there. So I'm the deputy director of that center. So I've been working with the infrastructure for high-performance computing in over 25 years now. So PDC is a supercomputer center. I will talk a little bit about that. I will talk about heat reuse. I will talk about liquid cooling and some case studies. So KTH is the largest technical university in Sweden, and PDC is the largest supercomputer center in Sweden. So of course what we do is to operate large systems, really large systems for academia in Sweden. So if you have the largest technical simulation problems, you come to us. And it's free for Swedish academia to use our facilities. So, because we get most of our funding from the Science Council in Sweden to support the research in Sweden. We also have some industrial collaborations, like Scania is one of our big collaborators. So I've been talking about supercomputers. So this is a short presentation of how a supercomputer is done. So a supercomputer today is not any form of special electronics. It's a cluster, probably a big cluster, but a cluster also with high performance interconnect. So you have a very high bandwidth in the local area network in the system. And as you know, the system is built out of nodes, which are similar to PCs or something like that, and each node has a couple of processors, and each processor has a number of cores. So what differs from our nodes from PCs is that they probably have a little bit more processors and a little bit more cores. So just to give you an example, so this is our main system at the moment, which has over 1,600 compute nodes. And we're talking about the peak performance of 2 peta operations, floating point operations per second. And it has a lot of memory, a lot of cores. So we're talking about over 50,000 cores for this system. But maybe in this presentation it's more interesting to know that it takes around 600 kilowatt to run the system. So each rack is roughly in the order of 60 to 70 kilowatt. And that's only the beginning of the development, I would say. So our friend from Volvo talked about he was impressed by 30, but each rack here has 200 ampere connections, so it takes a lot of power. And I'm coming to how we take care of that and what we do with it later on. A little bit about the background at PDC. We are located in the middle of Stockholm. We are between the Royal National City Park and the city center, so we are in a very attractive area of Stockholm. That means also that the buildings are listed, so we cannot change anything of the exterior of the buildings. So that's one of the reasons we have been using district cooling, which is available in Stockholm, and we've been using that in many years now since we moved into this facility in 2004. During the years, district cooling has been changed a little bit. Previously it was very expensive, but now you can also get refund for the energy you use. I will not go into details there. But also you need some to have a decent reliability. You need some backup cooling as well, because the district cooling hasn't been on that reliable yet. I think they are working on improving that, but still you need some backup cooling. So we have complete backup cooling for everything we have. So if you take a look on the energy consumption, you see this is the energy consumption for our center. So we started in 2004 in this building. We talked about 200 and 300 kilowatt, and that is increased now to 1.5 megawatt. So it's quite a dramatic increase in the consumption, and we are doing that basically with the same building, with the same space. So we have only a computer hall of roughly 200 square meters, a little bit more, and we have probably a little bit more also from surrounding sort of technical areas. But it's a lot of power in a very small room, so we have high density, very high density. So that is one reason we are looking into liquid cooling, and also the energy consumption is fairly expensive for us. Only for this small, very small center compared to the industry, we're talking about roughly 1 million euro per year in energy cost. So in 2009, we were about to buy a new computer system, and we had the idea to reuse the energy in some way to save the environment and to save some money as well. And we looked on the market, and the machine we choose, this was a Cray called XE6 at that time, which is sort of a little bit fancier cluster as well. Didn't have a good liquid cooling option at that time. So we decided to do something ourselves. So we took an air-cooled system and retrofitted that with a water cooling system on top. And we selected one building at KTH. It was the chemistry laboratory, which needed a lot of air, because you know the chemical fumes needs a lot of ventilation. So what we did was to heat the incoming air to this building, because they need a lot of air because ventilate out the fumes. So this is a little bit about the background. But the entire thing is to be able to collect high enough temperature to be able to reuse the energies. So in this case, you need at least something which is above 20 degrees. The incoming air to a building need to be at least, normally like 20 degrees in the room, right? So we need something which is a little bit more than that to be able to transport it away and to heat the incoming air into the building. So we need 25, 30 degrees from the computer itself to be able to reuse it for this purpose. In other purposes, I mean, if you're using radiators or something, you probably need a much higher temperature. But if you're heating the incoming air, or maybe circulating water in the plates, 20, 25, 30 degrees is sufficient. So we purchased the air-cooled version, and we did some retrofitting on that ourselves. So we did place industrial heat exchangers above the actual Cray. The Cray system sent out this hot air up on the upper side of the cabinets. They take in cold air from the raised floor and send it up right out in the air. So we built some chimneys and placed heat exchangers on top of the cray. And that worked fairly well. It had worked very well for 4 years. As you know, computers get old very fast, as your laptop does. Also, our supercomputers become old very fast. So after 4 or 5 years, it's not economical anymore to run them. The energy cost becomes too big factor in that. And after 4 or 5 years, there is a new system which costs the same amount but has a capacity which is much larger, exactly as your other computers. So this is a little bit more about the temperature in the system. As we mentioned, we have the raised floor here. We have about 16 degrees under the floor. The racks has fans in them, and they sort of sucks up air from around below the air, and out comes something around 44 to degrees Celsius. And we collect that with the chimney, and the air goes through the heat exchanger and comes out, and is room neutral again with 21 degrees. And we get out water which is around 30 degrees, which worked really good. And this is just to show you the building we were heating. So fortunately, there was a water system already at KTH. It has been there for many years, so there is a district or local district heating system, and there is a local district cooling system in our campus. So by being a little bit smart, we could actually use that. So this is where the computers are. Here's our building, and this is the chemistry building. But being a little bit smart, we could use the existing piping network and building sort of a closed loop. When we're running the recycling, we can form a closed loop at KTH, but just installing some you close it off at some points. If you like more information about that, you can discuss that later, because it's a little bit hard to explain in detail how it works, but it worked really fine actually. And this is also a diagram about in the computer hall. We also have normal computer room air conditionings, and we have the cray system, which is now retrofitted to liquid cooling. And to be able to have different loops, we had 2 cooling loops here. One which is normal, or maybe normal, but in our house we have 8 input and 18 output Celsius for the crack units. And for the cray system, it's like 19 or 33 or 45 degrees output. So of course we need separate heat exchangers for that as well. So those heat exchangers are one mainly for heater use, one for the normal district cooling, and one extra for redundancy, where we cool it by just using tap water in this case. So there are 3 different circuits. And this are the heat exchangers. As we are very low on space, we have been forced to use a very dense design of it. So you can see it was very hard to do this. for the plumbers. And this is the actual system, so you have the racks of the cray, and you have the heat exchanger above, and you can see the plumbing coming out of it. So we used that for 4 or 5 years, and it worked fairly well. As I said, of course, it was some problems when we built it. It's sort of custom made, needs to fit exactly on the system and all that kind of stuff. So all the computer vendors didn't really, even if they were very supportive, it was very hard to find all the correct information from them, I can say. Both for simple things like exactly the size of the top of the rack or something like that, it was very hard to find out because they weren't really used to that question. No one had ever attached a chimney to a system of this form before. So what we like to do is reuse existing infrastructure like the piping network. We also understood that this is a very different perspective of timing in the computer industry and the building industry, which doing the sort of heat reuse stuff normally. So in the computer industry, we can install the system very fast, but it takes a very long time to build the sort of infrastructure around it. Because that is sort of, I mean, people who works with buildings normally have a perspective. This will last for 50 years. If it takes 1 month more, doesn't really matter. If it takes 1 year to calibrate the system, it's not a big deal for the building industry, but for the computer, I mean, it's 1/4 of the lifetime. So that's something you have to keep in mind if you're doing special jobs like this. So we did some evaluation during the winter 2012 and 2013. So this shows the kilowatt reused, and this is an inverse scale of the outdoor temperature. So it's very linear with the outdoor temperature, as you can see. There are some days missing recordings because of some fault in the system, but the days we have is very sort of linear with the outdoor temperature. Of course, colder temperature means more possibilities for heat reuse. So, but we have the totals, and we saved quite a lot during those years we ran the system. But of course, in 4 years, we could hardly motivate these investments. You need to have an infrastructure which can last more than 1 computer generation. So we are talking about payoff time of 7 years or something like that. So you need at least the second computer on the same infrastructure, more or less, to be able to pay off. And we have actually done that as well, but now we have changed a little bit. The second computer we have been doing was also actually a Cray. Now some people think that we are always buying a Cray system. That's not true. We have bought a lot of different systems during the years, all kind of vendors. But if you buy something 2 times in a row, people think that we are sort of stuck with them, but they are doing pretty good computers. So this is a system we installed sort of 1 year ago. It has about the same power consumption. We're talking about 600, 700 kilowatt. But the capacity has now increased 6 or 7 or even 8 times, depending on a little bit on what you measure. So in 4 or 5 years, the capacity, and this is the same cost, same everything, same size. Capacity up 8 times. That's not too bad. But now also Cray has done a decent job with the liquid cooling system, so we could buy ready-made system out of the box, which is very nice. We didn't have to adapt it ourselves anymore. And the Cray XC40 has sort of a hybrid cooling, so the actual CPU boards, they are cooled by air, but each rack has a built-in heat exchanger, and you also have special fan racks, blower racks as they call it, between the CPU cabinets. And you can see it in this slide. So air comes, you have a row of racks. So we have total 9 racks. And the air flows through all the racks. It comes in one end and comes out in the other end. It has the same temperature when it comes out as it comes in. And that is because you have, in each rack, you have the heat exchangers. So the boards are cooled by air. So the air is warmed up in the CPUs and cooled down in the heat exchangers. Very neat. But it's principle the same as those back doors on cool doors on computers. It's the same principle. So it's a mixed kind of hybrid cooling. What has changed also is that now KTH has just installed a central heat reuse facility, which is reusing all the waste heat from KTH. To a large extent, that is coming from our computer or other computers in our computer. We're talking about more than 1 megawatt here. So I guess this is about half the energy which is reused. Other reuse is from laboratories, but also from offices and things like that, which are cooled during the summer. And the heat coming to the heat reuse facility is only 70 degrees because they are mixing the water with low grade and a little bit higher grade. So it comes to the heat use facility, it is only 17 degrees, but they have installed 2 heat pumps in series, so you can increase the temperature to 70 degrees Celsius. And then now heat pumps has become really efficient, so it is thought to be worthwhile in a number of years as well. And as I say, supercomputers are really good heaters because we don't have much variation in the load. Our users stand in the queue to be able to run, so we almost always have 95% usage of the system, so it's very stable. So they produce very good heat all the time, around the year, which is good. You don't, maybe not so good in the summer because we don't need the heat at that time, but in the winter it's very stable and easy to understand what's going on. So about 1/4 of the energy to KTH heating is supposed to be saved by this arrangement, and about half of that is coming from the computers in our computing center, and that is also, of course, some CO2 reduction. So that is what I'm basing my experience on. Now I will talk a little bit generally about liquid cooling and also some other experience from some use cases, different kinds of cooling and liquid cooling system and heat reuse. Heat reuse is, of course, not the only reason to use liquid cooling. So there are many good reasons to use liquid cooling. We have been talking about the environment and the cost, total cost of ownership, but there are also other kind of factors. We are talking about the stability of the system. If you have water cooling, you normally can operate the system a little bit higher clock frequency, for example, because the cooling is more stable. If you only are using liquid cooling, you can also have a very silent computer room or computer installation, which might be nice in some applications. Of course, it can be more efficient because the fans which runs all the air in the normal computer hall, that will produce or take a lot of power. Actually, water pumps are often taking less power than the fans for the same kind of cooling. And of course, if the air is not clean, you don't have a problem with that if you are using liquid cooling as well. So there are many different factors. So I got this slide from Isotope, which is a liquid cooling company, the other day, and they have a good classification of different kind of cooling. So we're talking about air cooling. We are talking about indirect liquid cooling, which is the hybrid cooling, for example, with the Cray system we have today. We are talking about direct liquid cooling, where you actually cool the CPUs directly with water or some other liquid, where you have pipes out to the actual circuit boards. And they also have total liquid cooling, where everything is liquid cooled. In some cases, you have 90-95% of the system liquid cooled. But if you have total liquid cooling, everything should be sort of liquid cooled. A problem with liquid cooling is that there are very many kinds of water requirements. Each system has its own water requirements, which is a problem. There is an organization in the US called ASHRAE, which sort of tries to classify water into different categories, and you have different temperatures and for different applications. But not everyone follows this, and each computer system has its own today sort of characteristic for the cooling, pressure, temperature, and all that. It also demands on the cleanness of the water. So that is a little bit of one of the problems. But also connectors and how you pipe things is very different in different applications, different systems. So it would be nice to have some kind of standardization, but that probably takes some more time before it arrives. But as I say, direct liquid cooling is fairly well established today. So many of the big vendors, computer vendors, can provide systems which are directly liquid cooled. And I will mention a few examples here. And I think I already mentioned some of the benefits of liquid cooling. And of course, you more direct you have your cooling, you higher temperature you can get out. You should sort of try to capture the heat as close to the source as possible. And that is also when both if you have air or liquid cooling, the closer to the source, you can capture the heat better because you can get out better higher temperatures. We are talking about a little bit about PoE before, and I would say today PoE has sort of lost some of its value. Many of the new computer halls are really good. You have a PoE of 1.1 or 1.2 or 1.3. It doesn't really matter so much. I would say that heat reuse is much more, gives much more bigger savings than trying to improve the PoE anymore. So I have told before that we haven't even calculated the PUE on our computer center. People are shocked by that, but it's much more interesting to see how the economical heat reuse is contributing to a good environment. But there are also some, of course, problems with heat reuse. We are talking about computers' short life cycle, and we don't have any standardization, so you might need to change some of the infrastructure when you upgrade the computer, if you change to another manufacturer, which might be a problem. There is also a problem with corrosion and bacteria in hot water. Not an easy problem. We have seen that problem. Abroad, you normally have some kind of chemicals in the water. We try to avoid that in Sweden because of environmental reasons, but you can get some corrosion problems and things like that. And doesn't seem to be any consensus in the business how you should treat things like that. There's sort of more black magic methods than real scientific methods how you should cope with that, as far as I understand. We have been talking about capturing the heat close to the source. Of course, if that's the best done by direct liquid cooling like this image where you see the CPUs and you see the copper tubes going out to the heat sources. If you don't do that, it's probably better to encapsulate the heat in some way to take it as close as possible to the source, as we have been talking about before. So this is a case study of a computer system from HP where they have taken a lot of measures to reuse the heat. So this system has been installed in one of the largest computer installations in the US and been very good on producing hot water. So here you see a CPU board, and you see there is on the CPU board there is a heat pipe going through all the more active components. And the heat is then transferred through this metal plate, metal to metal. So when you insert this into the rack, the heat is transferred to the rack sort of a cooling loop by using this metal to metal connection. So they clamp it into the rack and transfer the heat. Of course, you lose a couple of degrees of temperature on that. Every sort of connection, you lose something, but it gives you a quite big flexibility to service or maintain the system. And here you see the boards connected or being connected by the racks. So you see it, there is a lot of those CPU boards in one of those systems. And this is the back of the system where you see the water coming in. It's a quite dense system, so it's something quite interesting to look at. Another innovation they have made, or innovation is not revolutionary, but they have a sort of modularized plumbing system. To be able to install this, they have also a plumbing set. So this is the plumbing set for one rack, I believe, or two racks. So you purchase a number of those and connect them together, and it fits exactly into the computer. So when you do the installation, it's fairly fast to do. You don't have to do a special custom-made installation. You just take this system with all the components and install it under the floor. I'm going over to another kind of cooling system. So we have been testing this as well at KTH. We didn't purchase anything at the end, not because it was bad, but this is mineral oil cooling. So you have sort of a bath tube where you sank down your computers. It's submerged in the fluid, and you have a special box here which sort of pumps around the oil in the bath tubes, and also have a built-in heat exchanger, so you can water cool that. The mineral oil is good because it doesn't destroy the electronics, but of course moving parts has to be taken away. For example, if you have a fan or something like that in the system, or also a moving disk which is not completely sealed, that has to be taken away. But the cooling is really good, and you can get a really hot temperature out of this. So we could easily get out 60 degrees Celsius water from the heat exchanger there. So it has very good potential to be used in heat reuse applications. So if you can get out 60 to 70 degrees, you can use it directly into radiators or something to heat the buildings. Though it's a little bit hard with the maintenance. The boards get quite messy, and it is not really that dense because the bath tubes cannot be so high. In principle, they probably could, but out of practical reason, you have to be able. You need to raise up the CPU boards from the tubes, which makes them a little bit low. But it's also a question of getting maintenance out in the field. Another fluid or set of fluids is the 3M Novec stuff, which also is dielectric, and things can be submerged in that as well. And it can be also based on the same principle as the oil, that you just circulate the liquid instead of the oil. Or you could also have a two-phase system where you sort of boil the Novec. So if you choose this kind of Novec, you have a boiling point of 49 degrees Celsius, and the CPU is hot enough to sort of getting the fluid to boil, which gets a very good transfer of heat as well. So I have a quite fun example on that here. So this is a simple box with a very high density CPU on, and they have just taken sort of an ordinary water cooler here, and filled the box with Novec. Novec is very expensive though, so it's maybe not that economical, but it's a really nice experiment. And I can see if I can run the video here, maybe not. I could, minutes ago, I could do it. But I can't do it anymore. But you can believe me that you see the boiling here from the plate. I don't know why I can't do it anymore. I could, just minutes ago, I could do it, but let's skip that. We'll have similar companies like Isotope, which has a special box where they have either Novec or some other fluid. So in this case, you have sort of a special made box, and you have the box filled with Novec or some hot plates, and you can just insert water and get out water which is really hot. So that's another kind of same kind of idea, but you don't submerge standard components here. You have a special box which you are filled with this kind of fluid which cools the components. And they have a design also which is fairly similar to the HP solution I was talking about. So they have a number of those boards in a container here, and they cool this with a metal-to-metal transfer system as well, and you have an outer loop or several outer loops of circulating fluid. So this is a system which is totally liquid cooled, so no energy is going out to the air almost. And might be good in certain applications. I mentioned that in our campus or my computer hall, we have racks with 70, 60 kilowatt. But there are much higher densities coming on the market today. So I think this was on a photo from the last supercomputing show, and they showed a system which had 400 kilowatt per cabinet. So that's maybe giving some ideas what is coming. And tomorrow I will go to this year's supercomputing show, and I guess they will even get higher numbers this year than they had the previous year. So I will come back to you later on to tell you what kind of densities we can expect in the future. And this is, of course, achieved by having a lot of accelerators in the system. You also get a very high peak performance, 1.2 petaflops per rack, but also at the cost of a very high density. And of course, this is liquid cooled from the start. So to summarize the situation about liquid cooling is coming fairly strongly. There is a lot of products available today, not much standardization, so we lack standardization about water temperatures, water quality, connectors. But as I mentioned, ASHRAE is doing some of the standard work, not only on the temperature, but also on the water quality stuff. So they have a lot of white papers which are worthwhile to read, actually, if you are going into liquid cooling. So I can recommend that. And I think liquid cooling for high densities will come quite strongly in the future.